Trig equations. So let's start off writing down our trig cheat sheet, or our trig reference sheet, if you want to call it. We'll write down our two reference triangles. These are going to come in handy quite a bit today. So 1, 2, square root of 3, 1, 1, square root of 2. That guy. We'll have this diagram. This is a positive, negative diagram. And then what else do we have? So we've got...
Can you explain when that ASTC diagram applies?
Sure. We'll talk about it today. Cosine x squared plus sine squared x equals 1 is the Pythagorean identity. There's a few other Pythagorean identities. Then we've got positive and negative, as well as the cofunction identities. I'm not going to write those down since we're not going to get into that today. Maybe on Monday. On Monday, we'll probably write out all of the trig identities, because the problems we're going to get into today are going to be very basic introduction to how to solve a trig equation. And then we're going to add layers on top of that. And those layers will start to include solving trig identities and factoring trig identities first, and then solving equations after that. All right, so let's talk about the periodicity of trig functions. If we have an angle, and it doesn't matter which quadrant, so let's just say it's over here. So let's say we have an angle theta. When we want to compute, say, sine of theta, we draw our reference triangle, dropping an altitude to the x-axis, our perpendicular here. We determine the side lengths. Either we're given a couple of the side lengths, and we have to find the third sometimes, or we're just given all of the side lengths. And remember, we can always solve for those with the Pythagorean theorem. And let's say if we want to compute sine of theta, we just use this triangle and compute sine of the reference angle, which is this angle here. And we get y over r. And of course, in different quadrants, y could potentially be negative. So the sine will be taken into account as well. However, our domain and range for sine and cosine are all real numbers, right? I can plug in any number into theta, no matter how big, doesn't matter. And as we saw when we first started looking at angles, that we often have angles that we call coterminal, meaning that this terminal side lines up, except that perhaps on a different angle, it just wraps around the circle more than once. If they are coterminal, at least in this case, then the angle is theta, and then what did we do? We added 2 pi radians to that by going all the way around. And so if we wanted to compute sine of theta plus 2 pi, what do we get? Well, the process is the same. It doesn't matter how many times the clock hand wraps around the circle. All that really matters is its ending position and the reference angle that it makes with the x-axis. So we get the exact same value when we evaluate sine. And we could repeat this. I could wrap around again and again and again, however many times we want. We could also go the opposite direction. So I could have got started at theta and then go minus 2 pi. to wrap around in the opposite direction. And we would still have a coterminal angle, which results in the same reference angle in the same quadrant and will give us the exact same trig ratio. So we write this by saying that sine of theta is equal to sine of theta plus 2 pi k. And likewise for cosine. So what do I mean by this? The k we consider as an arbitrary constant, but it takes integer values, positive or negative. So we usually denote it something like this, where we list out the numbers, some of the first few numbers, positive and negative, and we put dots in either direction to indicate that it could keep going. We can plug in any integer value we want for k there. In words, we say that the period of sine and cosine is 2 pi, meaning that every time we add an integer multiple of 2 pi, we're going to get the same value, because all we're doing is wrapping around the circle. We're still ending up with that same reference angle in the same quadrant. And so this is something we're going to have to consider now when we take a look at trig equations. And it's going to get even more complicated once we start adjusting trig equations where the argument isn't just an angle, it's 3 times an angle or something. So let's take a look at that. We'll talk about the period of tangent. Tangent's actually a weird one because the period is just pi. But since we don't have time to do that today, we can talk about that on Monday. So let's take a look at a basic example of a trig equation. So just give a general statement of solving the equation. Sine of x is equal to negative 1/2. So with these problems, with a lot of other function problem solving process, I like to kind of write out steps to try to help you guys keep your step in track, because especially if you get lost during one step, or if one step is really complicated, sometimes it can help to go back and remember where you're at. It's easy to lose track of what step you're on if the problem solving process is lengthy. Unfortunately, we're going to have a lot to add to this list depending on the complications that appear with these problems. So instead of putting numbers, I'm going to go ahead and just put things as bullets. And with a problem like this, the first thing we want to look for is determining the reference. So I should state that this is kind of the ultimate goal of where we want to get to in our trig equations. Just like with logarithmic equations, exponential equations, what did we want to do? We're trying to solve for a variable that appears inside some family of functions or some function. And so in order to solve for that, we often isolate that function by itself on one side of the equation, just like we did with logs, just like we did with exponentials. This is kind of the first goal of our trig equation. Sometimes the expressions will be more complicated. We work ourselves down to something like this. And once we get to a statement where trig equation is equal to a constant, that's kind of the hump of the problem. Once we get over that hump, the end is essentially in sight. And we just have a few more steps that remain. So our first step, determining the reference angle. And to do that, we're going to pull up our sheet. Let's try to get it all on the screen here. And what we want to do is look at our reference triangles. Whenever we are determining a reference angle, ignore the positive or negative. The only thing that matters is the ratio. So we've got a ratio of 1/2. Positives and negatives we'll get to in the next step. So you want to look at your reference triangles. And actually, let's draw two more. So most often, almost all situations, you're going to be using one of these two triangles. However, there's always going to be a handful of the degenerate triangles that appear. So for example, if we had a 0-degree angle, it would look maybe something like that, where these two sides should really be attached to each other, and this vertical side really should only have a distance of 0. And then the hypotenuse and the adjacent side to the angle are the same. They're both 1. So that's one degenerate angle. There's another degenerate angle at each of the quadrantal angles. So the other one, we can approximate pi/2 reference angle, having 0, 1, and 1. And of course, if it's in a different quadrant, the negative x-axis or the negative y-axis, you just make the one that is not the hypotenuse will then be negative. And we can compute any trig function based off of those triangles as well. So maybe we'll draw those in for this section of our trig, since those might come up. But anyway, if we look at what we have, our ratio that we're looking for is 1/2. So we're not going to be using the degenerate triangles. We're going to use our primary two reference triangles. You want to look which one has a ratio of 1 and 2, or which one has the numbers 1 and 2. And it's clearly going to be our 30, 60, 90 triangle. And so we need that side divided by the hypotenuse to get 1/2. And so all you have to ask is, well, how do I get this side divided by 2 for a sine? So sine is opposite over adjacent, and we look, that's going to be this pi/6 angle, because sine of pi/6 gives us 1/2. Everyone see that? So that determines our reference angle. Pi/6. Now what do we want to do? We want to pay attention to this minus sign. And this is where we're going to determine the quadrants. And so this brings up our positive negative sheet. The all seniors take calculus diagram. This is what determines the quadrants. So this minus sign in this diagram will help us figure out what quadrants should these angles be in. So if we look, since sine is negative, we want to figure out where is sine negative. So remember, A is all functions, all trig functions are positive. Second quadrant has an S, so sine is positive. And so since sine is negative, we want to be in the third and fourth quadrants. So I'm going to write that down. So we determine our quadrants. We determine 3 and 4. And so now what we have to do is determine the solutions. Let's say figure solution. So what do we need? We need a reference angle of pi/6 in quadrants 3 and quadrants 4. So this is where the counting in fractions of pi might come in handy. Maybe we can write that on our notes somewhere in our problem solving. So since our reference angle is pi/6, denominator is 6, pi is 6 pi/6, 2 pi is 12 pi/6. Good to keep handy. And so when we draw our diagrams for our solutions, what do we need? we need an angle in the third quadrant with a reference angle of pi over 6. And then we need an angle in the fourth quadrant with a reference angle of pi over 6. But we don't want to put the reference angles, we need to put the absolute angles, so the actual solutions. So from standard position, we are wrapping around how much? We are going halfway around the circle, 6 pi over 6. Then we have to plus, and keep wrapping around, pi over 6. So 6 pi over 6 plus pi over 6 gives us 7 pi over 6. As the first solution. And then the second solution, how do we count this angle? Well, one way to do it is we're going all the way around the circle, 12 pi over 6, and then back 1. So we are at 11 pi over 6. So with this step, maybe we should have said like figure the initial solutions, because this isn't just the general solution. This is just a specific 2 that we want to start with, because what do we know about sine and cosine? They are periodic functions. So any angle that is coterminal with these two angles will also have a sine ratio of -1/2. And if we wanted to fill in the sides for these triangles, because we get that negative because we're going downward in the y direction. So how do we find the general solution? We need to include the periodicity. Because 7 pi over 6 is a good answer, but what happens if I add 2 pi and go all the way around? Well, we'll be right back there in the same coterminal angle with the same reference angle in the same quadrant, and so we'll have the same sine value. So we actually have a lot more solutions, infinitely more solutions, to be exact. So what we want to do is add on 2 pi k, where again our k is any integer. This is what we call the general solution. This hits all of the solutions. So how would I find a specific one? We can start with either of these angles that would correspond to that specific solution, and then determine how many times we need to wrap around the circle. So for example, oftentimes what the problem might state is find the first 4 positive solutions. Or it could say find the first 2 positive, find the first 2 negative solutions. So remember, our k values can be negative. That just means we are wrapping around the circle in the opposite direction. So how do I find the first 4 positive solutions? Well, since the reference angles we started with, or the initial solutions we started with, are positive, we can essentially start with those. If we are wrapping around the circle in our positive direction, then the first angle with a sine ratio of -1/2 is 7 pi over 6. We then keep wrapping around the circle, and we see that the next angle with a sine ratio of -1/2 is going to be 11 pi over 6. and then we need 2 more. So we're just going to keep wrapping around the circle. So now how much am I going to be when I get back around here? Well, if I start here, this was 7 pi over 6. How do I get back? We have to add 2 pi. So the next solution is going to be 7 pi over 6 plus 2 pi, which I'm just going to write as 12 pi over 6. So our next one is going to be 19 pi over 6. And then what's the next one after that? It'll be back to this reference angle. And this guy was 11 pi over 6. So when's the next time we will be back here? 11 pi over 6 plus 2 pi. And so those are our answers. Any questions on that? All right, so real quick, we'll talk more about this on Monday. What can happen now is we can either complicate the end part of this problem or the beginning part. So where we just started, that was kind of like the middle of most of these trig equations. If we were to add steps on the end, the problem might look something like this. We're changing the argument. Essentially what's happening is we're almost like stretching our axes and then wrapping it around the circle faster than what it should be, 3 times faster. And what's going to happen is this is going to affect a lot of the solutions that come about. So you can kind of think about this as just being a substitution. Let's say we have some angle that is related to a different angle. So we have an angle x and now an angle theta. And theta is just 3x. And so what did we find in the last part? We found, well, this just says sine of theta equals negative 1/2. We found the solutions. But this is the solutions for theta. We actually need to solve for x. And so what we'll have to do to solve for x is essentially take those 2 sets of equations It's 2 pi k there. Getting ahead of myself. And I didn't write this letter. Rewrite that one. So 3x equals 11 pi over 6 plus 2 pi. So we would take these 2 equations now and solve for x. Meaning we would divide by 3. And that's going to affect the constants as you would expect, 7 pi over 18, 11 pi over 18. But it's also going to affect the periodicity. Since the period of sine is 2 pi, what's going to happen if I do a horizontal compression by a factor of 3? It'll shrink the period by a factor of 3. And so we also have to remember to divide this 2 pi k by 3 as well. And that's going to throw a little bit of a wrench in some of these problems, because if we have to answer, say, find the first 4 positive solutions, they're going to look a little weird. The angles aren't going to be these traditional angles we've seen of pi over 6, pi over 4. Because we're dividing those by 3, the solutions can be different denominators, and there can be multiple solutions within a given quadrant even. So we'll talk about how to do more of that on Monday. Any questions?